We are continuing in 14.1 on functions of several variables. Let's take a look at level curves, and then we'll get into a number of definitions we need for the rest of the chapter, or book for that matter. So let's look at what a level curve is. Let's look at this example. So for example, let's let f of xy equal 9 minus x squared minus y squared. Okay, and this time we're going to restrict the domain. So restrict the domain to D equal to the set xy such that x squared plus y squared is less than or equal to 9. So basically what that's going to do is chop the graph off at the xy plane. So it's not going to continue. So we can look at a few things, like the domain is that set of values. I'll just draw a little thing here for us. Close enough, right there. So that's going to be everything on the inside, like that. Origin radius 3. Okay, so that's the domain. That's my D. So what we want to do is let me go ahead and sketch this over here. So let's sketch that graph. That we know what that graph is. I'll try to make it a little bigger. So kind of see what's going on, hopefully. So here's my X and Y and Z. And so we're up at 9. So let me see. 2, 4, 6, 8, 10. So here's 9. It's pretty close, huh? And then I have my paraboloid going down like this. Maybe something like that. No, that doesn't look too good. Let's try that again. So it's going to look like this and like this. And so you hit basically that circle down here. And so it's looking like that. Stopping there. We'll just do like a sketch. You can just sketch these sometimes. Right? You can sketch them going in your erase later, and then the back can be dotted. So that's fine. You can do stuff like that. You can make it look a lot nicer if you want, but that's, you get the idea. So that's my paraboloid that opens down like that. So then what you do to make a level curve is we go in and we say let z be different values. So we're going to say let's let z be 0, which of course is the xy plane, right? And then we'll do z equals, and then you do your steps the same amount. So you step in 2s. We'll do 2, 4, 6, and 8. And I'm not going to draw it like really to scale exactly because it's tough to do that. But the book has exactly the same one. When you do that, though, those are like, think of those as planes at 8. So 8's way up here. So it's a plane that's cutting through. If you cut a plane through that, the paraboloid, it's going to create that circle up there. So these are going to be circles. But what we're interested in is, what if we look from the top and project that down into the plane? So what you get then is x squared plus y squared equals 9. So that's a circle down in the xy plane. you get x squared plus y squared equals 7. You get x squared plus y squared equals 5. X squared plus y squared equals 3. And then x squared plus y squared equals 1. And so what you're getting then are these circles up on the surface. You're getting that one, and then, where is it? At 8 was that first one up here, and then 7, right, and then 5, and then down here, right? So you're getting those circles. So if you project them down, what you will see is in the xy plane. So we're going to put this in the xy plane, and I'm not going to do this totally to scale and actually count values. But what you basically get then is you get this circle like this. Let's copy that. Copy. And then you paste it. And then you get another one, but it's smaller. But it's, when you first do it, it's going to be kind of close to it, like that. And then, paste it again. You get another circle, but it's even, so this one, these are like, maybe like that. I'll try to make it a little better what I'm trying to show you. So I'm exaggerating a little bit here what's happening. Okay, so those are close together, but then as you get in closer and closer, they're not going to be as far apart. They're going to be farther apart, like that. So because what we know is on the outside it gets really steep here compared to the inside. So these inside will be farther apart when you project it down. Right, so basically this one is pertaining to this one, and then this one is pertaining to this one. But then as you get on the outside, these right here and here will be these. So they're closer and closer together. This is like what a topological map looks like. It shows the contours. So this is like a contour map. So like, I'll just say like a contour. Or topological map is what that is. So those are level curves. And then the next one we'll look at, so these are, well, when I do that, that's when we refer to level curves. And you could, it's like you have level curves that you can consider them in the XYZ plane, like up on the surface, or you project them down at the XY plane like that. So this is where I usually pull out a topological map and show it to you and see how the curves, what you basically get if you're getting those type of maps. If you see these contours like this and then they get, like suppose they start getting really close together, then you know something's really steep. So that might be, you have to look at it closely, but this is either going to be a ridge or a canyon. And then you also see the ones, the peaks, let's see a peak like this, and then as you get closer, like it might show a bunch of them like this. And so that's probably a peak right there. And then that's the mountain going up. So that's the concept. Okay, so let me get rid of all that. Okay. Next is what if you had something like this? So suppose you had f of xy, xyz. So f of xyz equal to something. In this case, I'm going to say it's x squared plus y squared plus z squared. So we often use the letter W. That's like W equals x squared plus y squared plus z squared. And then if you do level, if you choose W to be something, say 2, 4, 6, 8, then you get level surfaces. So these are level surfaces. So the projection, it goes from 3 dimensions down to, down from 4 dimensions down to 3 dimensions. So your 3D level surfaces then will be 2 equal to x squared plus y squared plus z squared. And then 4 x squared, y squared, z squared. And then 6, 8, all the same, of course. So what type of surface is that, of course? X squared, y squared, z squared. Those are spheres. So those are all spheres. So your projection from 4D down to 3D are concentric spheres. So it can help you visualize a four-dimensional object, what that might kind of do somehow. All right, so that's what's happening. You have concentric spheres. Okay, next number of things are a bunch of definitions. And I like to go through these carefully because they're really important for theorems and hypothesis type stuff. And so you go to make sure you're writing them all down. So first thing is the definition of a delta neighborhood. So a delta neighborhood, and we're going to abbreviate this. We will abbreviate that as delta and then a subscript n, so for the neighborhoods. So delta neighborhood about, like around, x naught, y naught, so around a point, and this will just be in 2D, but you can have a delta neighborhood really any dimension. So it's around a point, for in 2D this case, is a circle, because it's in 2D, about or around the x naught, y naught of radius delta greater than 0. So delta neighborhood is the set of all points x, y, such that, and then basically the distance between x, y, and x naught is delta, or less than delta. So it's the square root of x minus x naught squared plus y minus y naught squared is less than delta. So you could talk about a delta neighborhood, really any dimension. You just keep going, basically. This just keeps going. And you get a sphere, basically a delta sphere, right? And then you could keep going to whatever dimension you're kind of want to talk about. So you got to picture what that's kind of referring to is this tiny circle. It doesn't matter the size, really, but that's essentially kind of what you're thinking. So here's your x naught and y naught. So what you get then are these circles, and you're not including the end, right? They're open. Okay, so there's your circle. Although think of them maybe smaller. I don't know, more like that. Okay, so that's what that is. And then there's your radius, there's your delta. So it's referring to all the points inside there. So you have all of those points are what's inside that delta neighborhood. All right, next definition, interior point. So now we build on that definition of a delta neighborhood. So these definitions use that to define things, basically about the delta neighborhoods. So here's the next definition. An interior point. So we want to talk about like what's inside a set. What do we mean by being inside of a set? So an interior point of a region R in the xy plane, I wrote that wrong, in the xy plane x naught y naught is an interior point. That's what I guess I'm defining now. If there exists a delta neighborhood such that all points in the delta neighborhood are in the region R, or in R. Okay, I'm going to start describing stuff over here. So basically it's saying it's an interior point, say here, if we can put essentially there exists a delta neighborhood around it, like that, such that all points are inside. So all of these points would be here, are inside our region R. Okay, so here's my R. And so is that little dot right there? Yeah, well, of course that's an interior point. If I zoomed in far enough, I could get a tiny little delta neighborhood around it, like that. It doesn't matter, I can't zoom far enough, but you can always do that. So that's an interior point. Okay. Next. Boundary point. So next definition. Boundary point. How should we define that? So we say the point x naught, y naught is a boundary point if any delta neighborhood centered at x naught, y naught consists of points inside of R and outside of R. So it's centered at that, and that consists or has points, consists of points inside of R and outside. Well, that makes sense, right? I mean, if you have a boundary point, like this is clearly a boundary point, right? And then if you put any delta neighborhood, any size delta neighborhood around this thing, then you're going to have points within it and without it. You can have points here and here. And it doesn't matter what size you make that thing, right? You're always going to have it. It's always going to be inside or outside. That's what we mean by how we can define it with a delta neighborhood. Okay, next. Next is definition of open. All right, so you've heard of open in 2D, or number line. So this is open for a region. So a region R, got ahead of myself again, in the xy plane, is open if every point in R is an interior point. So is open if every point in R is an interior point. So think about that. Does that make sense? So if you have some region, and let's change colors here, and you have so this is kind of supposed to look like an open region R. So if that's my open region R, then doesn't it make sense that every point you can put a delta neighborhood around it? So here, and you can put a delta neighborhood around it so that every point's an interior point. So an interior point means you can put a delta neighborhood around it and it's all within R. Well, that's what you want to be open. So think basically open interval like that. It doesn't include those endpoints. Same, but you can get as close as you ever want to those endpoints. So same idea. All right. And then after that, one more thing is closed. So definition. R, so a region R is closed if it includes all of its boundary points. So R is closed if it includes all of its boundary points. So you have to think of it as, we have to define the region somehow. So you know the boundary of the region. Do we include it or not, essentially? So this is when you draw it solid, basically. And we're going to include all those values, right? So there's my region. And so that's the boundary that defines R. And so then you have those boundary points here that are included. And again, you shrink any size, you have points within and without, or inside, outside of the region. Okay, so a lot of that definition stuff, I'm not going to ask you like repeat it or define it. It's just we're going to be using all those definitions when we start defining theorems and definitions later that have to do with open and closed and boundary and not boundary and stuff like that. Okay, there was one more that I think I missed because I just remembered. Bounded region. Yeah, I almost forgot that one. That one's back here. Okay, so last definition. Oops, let's change that. I knew I was going to start doing that at some point. So definition is this. So a region okay, and make sure I missed it. Okay, so two things, bounded and not bounded. So a region R is bounded if there exists a circle of finite radius that contains all of R. That contains all of R. Unbounded means basically just not bounded, right? So let me write that down real quick. So a region R is unbounded if R is not bounded. So not bounded means what? It would mean there does not exist a circle of finite radius that contains all of R. So you take any region, so take my region R. So does there exist a circle of finite radius? Well, of course there is on this one. I take a circle, all right, that circle, and I can move this nicely, like there, that contains all of R. That's all that it's all we mean here. Okay, so here's all of R, and here And that circle clearly has a finite radius, so it contains all of our, so R is bounded. So you have your radius here going out here, and then so that circle of radius, let's just say little r, is real, so it's bounded. One that may not be bounded, possibly, something like this, we could make it a region that's open. So here's an open region that's not bounded, but you can't, it's clearly unbounded, right? Because you can't put a circle around it, right? So this circle here doesn't include all of that. I mean, this keeps going like that. It keeps on going forever, so you can't do that. So that doesn't work. Okay, so that region, I might be referring to all of this, right? And it keeps on going. The arrows mean it keeps on going. So that's not a bounded region. Okay, now we have everything we needed for that section.